Howdy. Today we're going to cover not Kepler's law. Kepler's laws are not actually used in the AP Physics 1 exam, but dude figured out the planetary motion around the sun, and it's big time. But we don't cover his laws directly. So he found out that for any orbital satellite system, that the radius and the velocity and the period, they follow a very specific ratio. And so he was able to figure out, hey, this is actually a giant pattern, man, like clockwork around the sun. But it only really depended upon the magic universal law of gravitation, capital G, and the mass of the thing you were orbiting. So the massive objects in the center, like the sun, mattered, but the mass of the objects out there didn't. So same thing goes for a planetary system where you have Jupiter has many moons, right, going around, and so the velocity and the period and the radius only really depends on Jupiter and not on the moon, like Europa or something like that. So, anyways, Carl Sagan, the bomb, back in the day. He's got a video on explaining Kepler's laws in his own awesome, quirky sort of way. So if you want to watch that video, you can. That's where we got the ideas for these ratios we're going to talk about, but not really going to go into the actual laws themselves. Okay. So where are we going with this? So let's start off with deriving the period of the moon. So do you know, before we even start, do you know how long it takes for the moon to go around the Earth? Um, what's the period of the moon? So we know how long it takes the Earth to go around the sun, right? 365.24 something days, right? And but how long does the moon take to go around the Earth? So we're going to figure that out mathematically today. So let's talk about a couple things. Um, let us see where my no, Alt Shift T. Nope. Um, Alt T. Where to go? T. Well, I'm not sure what's going on here. Where did my where did my controls go? Let me go back here and see if my controls are over there. Yeah, they're there. Okay. Hold on. Okay, I think we're back. Right? We're back. Yeah, it looks like we're back. Okay. So let us start off with this idea where let me get a good old pencil. That's probably good right there. Let's use purple. I like purple. Okay. And let's talk about some of the ideas of centripetal motion, and gravity, and some of the things that we've derived already. So we know, for instance, that a centripetal force is equal to mv squared over r. We also know that a gravitational force is equal to capital G times the mass of one object times the mass of a second object divided by the radius between them squared. We also know that when we find out what a period is, it's related to velocity and radius, right? And so we found out before in the last quiz that your velocity will be equal to the square root of g times the mass of the thing you're orbiting divided by the radius. And so that's another thing we derived. We also found out that if you're going around one circle, you would do it in a period, right? And so our velocity is also one circle, which is 2 pi r, which is circumference, over capital T for period. And so these are all things that we know or have derived previously. So what does that got to do with this? Well, let's talk about this. First of all, we start off with this. The moon is going that way, but there's a force on it that way. And don't write FC here. It is an FC, but it actually is the force of gravity, which is causing this thing to go into this FC idea, right? That's really what FC is. The FC is the force of gravity. So let's talk about that. So here I'm going to write out mv squared over r. And don't you know that's the force that's making it, that's the gravity, but it's also a centripetal force making it go in a circle. Now, what is the centripetal force? Well, we just said that the centripetal force was gravity. So here, I'm going to write out G times M over R squared. So that's my first two equations. They are equal to each other, so I'm setting the two equations equal to each other. By the way, I'm going to call this little m, and I'm going to call this big M, right? A capital M. Okay, so what I'm going to do is I am going to try to solve this for V so that I can substitute the equation that has period in it, since I'm trying to get the period in there. Okay, so the masses will immediately cancel out because the mass on the left and the mass on the right, the small m is the moon, they cancel out. The radius is the distance from the Earth to the moon. So one of these radii will cancel one of these, and so it leaves that one there. And then I'm going to see that I have it in the format that I solved for last time, which was this format here. Let's see. G times the mass of the planet Earth divided by the radius of the satellite is equal to V. Now, what I want to do is I want to set it equal to this V because we already solved in an earlier thought process that one circumference over a period equals your period. I'm trying to get this into the form where I can have period in the equation. So this is 2 pi r over the period. Okay, now I want to solve this for t, but the problem is when if I think a little bit ahead, this is going to give me troubles. So I'm going to actually square both sides to get rid of the square root, because algebraically that will make my life a lot easier. Okay, so when I do that, that gets rid of this. I get g times m over r on that side. I just got rid of the square root. On this side, I get 4 pi squared r squared over t squared. Okay, now I'm going to solve for t. So when I solve for t, I get t squared equals 4 pi squared r cubed divided by g times m. And then I'm going to square root both sides in order to get rid of the square of the t. And so I get t squared is equal to the square root of 4 pi squared r cubed over gm. And now I have the actual equation for period. And I'm gonna try to do right now. I'm gonna try to do a kind of a proof of this. And so what we're doing here is we're gonna actually solve this for period. Okay. So the period is going to be equal to the square root of 4 times pi squared r cubed over g times m. And so that is going to be equal to the square root of 4 times pi squared. I'm just going to leave those because that's what they are, times the radius. Now the radius is going to be 3.9. I'm just going to do it the cheater way, E8, and that is cubed, and divided by G. I'm going to leave it as G. You got to know what G is, 6.67 times 10 to the 11th, times the mass of the Earth, which I'm going to cheat and write 6E24. Now, when you do that, you get a big number, and you're like, okay, I didn't, like, what is that? Well, that T is the amount of seconds that it takes to go one time around the moon, or one time around the Earth, right? But I have to I want to get into days. How many days does it take to go around the Earth? So what I do is I can divide that by 3,600 seconds per hour, and I want to get the days, right? And so and divide that by 24 hours per day, and then you're going to get the answer in how many days it takes to go around the moon. And let's see if you're right. So go ahead and put that in for the first answer, and we'll see if that works for finding the period of the moon.